So next, I'll be sharing you my lecture na muna. So start na tayo with the lecture. This is as soon as you learn how to do the non-isothermal reactor design for non-adiabatic process, which we will cover hopefully next meeting if we can do that. Okay, since the assignment is easy naman. So we can start with the non-adiabatic next meeting, so we can do a lot of discussion for this non-isothermal reactor simulation. Yeah. Okay, for your project. So let's start with the okay. Okay, with the lecture here. So I have the let's start with this energy balance. I prefer the lecture of Dr. Kraft from Illinois because it has the detailed ay hindi ko pala nabura yung part na to. Anyway, so I'll just start with this. So we will not be discussing that. So not thermochemistry for the non-isothermal reactor design. Everybody ready? So the major difference between the non-isothermal and that from the isothermal is that there's another equation that you will be needing taken from the energy balance to correlate the conversion as a function of temperature. Okay, so why? Okay, so we already answered that question. Okay, so for liquid phase reaction, again from say for this example, this is a liquid phase reaction, exothermic, so heat is given off during the reaction. So there's a process wherein heat is being released. So in your study of thermochemical chemical equilibria, you have seen that when heat is released during exothermic reaction, okay, if this heat is not removed, what happens to conversion? Conversion is low for when Q is 0 for adiabatic process. Okay, so for today, I will just discuss adiabatic, okay, adiabatic operation first. And so the thing about adiabatic is that the conversion is low. When you compare this with non-adiabatic process, wherein heat will be removed from the reactor as the heat is produced, there will be heat transfer. Okay, there will be cooling system around this plug flow, whether it is going counter current or co-current flow of fluid, of cooling fluid. So you can you will find out that the conversion is much higher, all right, if we have this type of system. For now, we'll have to do the adiabatic process. So you know the mole balance for the PFR. Again, this is a liquid phase reaction, and then the K is a function of temperature. Okay, then let's proceed. So the rate law for the reaction, again, is given, and for this case, this is KCA based on elementary reaction, the stoichiometry, and the flow rate, molar flow rate of A is based on the concentration, again, times that of the volume flow rate, volumetric flow rate. Okay, so this is a steady state process, so that the flow rate, volumetric flow rate, initial and final outlet will be the same as the outlets for the steady state operation. And then concentration, of course, from stoichiometry, so you know how to measure Ca as a function of the conversion and that of the initial concentration. That Ca is CaO 1 minus Xa. So 1 minus Xa represents how much remains after a certain conversion, Xa. All right? So that is the remaining concentration of A that will be leaving your reactor. Okay, in this case, it's a plug flow reactor. All right, so that's a measure of that. So 1 minus Xa. 1 minus the fraction that has been converted. Okay, conversion of A. So the remaining 1 minus xA is the unconverted or unutilized A. All right, so in short, so that is for the liquid phase. That for the gas phase, take note that you have to make correction for pressure and temperature. All right, so again, these are all based on the limiting reactant, which is there's only one reactant here, that is A. Now, if there are two reactants, take note that you have to know which is the limiting reactant. That is always based on the limiting reactant, the rate law. The concentration of the limiting reactant determines the rate of reaction. All right, so you have to define the rate law based on the limiting reactant. So in this case, this is A. Therefore, the rate law can be defined in terms of the conversion, wherein you have to represent CA as a function of conversion. All right, so once you're done with that, then you have to now substitute RA in this equation, then simplify, and also dxa, therefore. So everything here is a function now of conversion. So you can now differentiate the right-hand side with respect to the volume of the reactor, of the plug flow reactor. So you can integrate the volume from an initial volume, V sub O. And usually for a plug flow class, V sub O is the entrance, and then V sub O therefore is 0. And also at this point, the conversion is also 0 at the entrance. Okay, so you know that for our plug flow, as the reactant flows through the reactor, the conversion is variable. And with the non-isothermal, the temperature is also variable. Okay, so that substitution here represents this equation now. Since K now is a function of temperature, therefore, in this ordinary differential equation is not solvable because K is a function of T, which is a variable, and X is another variable. So this is not an ordinary differential equation. Now, to make this an ordinary differential equation, you need to have only one variable. So that you need to have T as a function of X, so that everything here in this ODE will be a function of only one variable. So once you have everything set as a function of X, so this now is solvable. You can now solve that ordinary differential equation because you only have one variable X conversion, because T now is defined in terms of X. And you can get that through your energy balance equation, that relationship of Tx. All right, so let's proceed to the next slide. Oops, okay, let me have my control. Next slide tayo. All right, so that's explained already in that presentation here. So K now will be expressed as a function of T using the Arrhenius equation. Now, usually the value of K1 is given at a given T1, and so at any given temperature during the reaction within the plug flow reactor, for example. So the temperature here will vary as you go from X1 to X2, say. So at this part of the volume of the reactor, temperature is T2. The reaction proceeds throughout the length of the reactor. You have T3 until such time that this is the final volume of the reactor, wherein the conversion is X final. And the final temperature will be T sub F. So this temperature here will be the changing temperature of your reactor, which is the variable function as a function of X. Variable as a function of X. Okay? It changes with X as you proceed with the reaction through the plug flow reactor. Questions so far, class? And so you have K1 given and T1. All right, so these are known values. So you just have to see how K, new value of K, varies with temperature. All right, so that's how you see the relationship of X to temperature. And then you can now measure the volume, the design. Okay, let's proceed. So energy balance. All right. So the concentration of a reactant in a feed stream, that's the inlet, will be greatly influenced by temperature when the reactant is. So can you answer this, anyone? When the reactant is gas, liquid, solid, either gas, liquid, or extremely viscous feed. Answer?
Ma'am,
Yes,
gas po.
gas. Very good. Because gas, of course, is always based on ideal gas law, always dependent on pressure, volume, and temperature. For liquid and solid, the pressure variation and temperature variation so far, for pressure, especially for pressure, it's not greatly affected by changes in pressure. But of course, for most chemical reaction, we try to keep the pressure as low as possible at standard pressure at 1 atmospheric pressure, 1 bar. Usually that's our pressure, unless it's a gaseous reaction. Mostly, of course, the pressure inside the reactor will change. But for most solid and liquid reactions, especially liquid, we rarely have solid reaction in reactor. So liquid reaction, the pressure is kept at standard condition at 1 bar at 1 atmospheric pressure. But for gas, of course, it changes also with pressure, unless the pressure is kept constant. So it depends on the process or design. Therefore, for a gas phase, of course, this is our concentration of species J at any given pressure and temperature. All right, so if pressure is constant, so we can cancel that. If temperature is constant, so T over T is. But in our case, of course, temperature is not constant, and we try to maintain a constant pressure within the reactor, okay, if that is possible. So our objective is finding the concentration as a function of temperature in terms of conversion as a function of temperature. So in that case, we have to keep our pressure fixed in order to study how temperature varies with conversion. So we have to keep this fixed. So we have to vary only our temperature. And so we have our C sub j as a function of conversion. All right, and that conversion is a function of temperature as well. All right, next. So in thermodynamics, closed system, okay, your reactor is a closed system for a batch, for example. Our general equation for energy conservation is that whatever is the change in energy of the system, which is this, the reaction itself, we're talking of, say, closed system, which is the flow of mass in and out is 0. There's no flow in and out for a closed system, but there's flow of energy. Okay, energy can flow. Okay, so whatever is the energy change within the system is due to the incoming heat and the work that is produced by the system. So incoming heat is positive. The inexact differential and inexact differential of work. Of course, inexact meaning Q and work are not state function, they are path function. So the changes, you have to take the total change in heat and work, and that's dependent on the path that they take, whether it's a constant pressure, constant volume, okay. So from an initial to a final state of the system. Okay, so you have to take the total change in Q and work. Okay. Our sign convention is heat flow to the system is always positive, and the work that is produced by the system to the going to the surrounding is negative. Work done by the system on the surrounding is always a negative work. Work done on the system is positive work. Okay, that's our sign convention. So negative work done by the system to the surrounding as heat is added to the system. Okay, so this is a general energy balance for closed system. Now, our reactor is an open system. Okay, our reactor is an open system. There are, unless it's a batch, okay, it's closed. Okay, for CSD, RPF, packed bed, membrane, bioreactor, where you see flow of mass in and out, so it's an open system. So heat can flow in and out. Each species, as an individual species, it carries with it a certain energy, and that energy in taken by the incoming species and the energy out due to the outgoing species. So there's energy input and energy output because of the incoming and outgoing species. And also there's a heat flow due to heat added to the system or heat removed from the system, or maybe work done by the system or work done on the system. So that's the energy flow. All right. There could be what we call energy production within the system because of the energy of the reaction. All right. So enthalpy of the reaction at a given temperature T. As the reaction proceeds, okay, heat will be produced. All right, during the reaction. All right, so heat will be produced during the reaction. That's why if you keep the heat inside, the temperature keeps rising or increasing, becomes higher and higher as you proceed because heat is accumulating inside the reactor. Okay, open system, there's a continuous flow or system. Masses crosses the boundaries. Mass flow can add or remove energy. Okay, that's the thing. All right, so let's see. Are you following this, class? Anyone familiar with this
Yes.
energy balance? Have you done energy balance in a reactor with an open system? Not yet?
No.
Well, not yet. Okay. Follow this discussion, class. This is understanding how temperature inside the reactor is changing with respect to the changing conversion. But in this case, we will be, assuming a steady state operation. So the rate of accumulation of energy. For unsteady state operation, of course, energy inside will be accumulated. So there will be increasing energy inside. Okay, rate of accumulation energy in the system for unsteady state. With time, heat will be increasing inside. So what about this? Heat input, okay, and there will be all the heat coming in. Energy input, okay, is positive. Work done by the system is always negative. Okay, let's do the energy balance. Okay, heat in, okay, heat out, energy leaving, energy added to the system. Say the system requires heat for the reaction to proceed, so it's endothermic process. Now, energy that is leaving the system will be carried out by the mass itself, and so that's leaving negative. Okay, so this is the total energy balance. So whatever is the energy that is accumulated within the system, so that includes, of course, the energy of the reaction. The energy of the reaction as the mass flow out of the system will be carried out by the flowing mass out. Okay, so that's the energy of the reaction. That's why you don't see here energy of the reaction yet. Okay, so this is the macro scale energy balance. So you don't look at the energy of the reaction as part of this overall energy balance for the system. Okay, but later you can define this energy of the reaction. It will appear later. So the rate of accumulation of energy in the system will be how much energy is accumulated within the reactor with respect to, in this case, time, of course. Okay. Now for adiabatic, we say that the temperature inside continuously increase and the accumulation of energy is assumed to be increasing as well. All right, so let's see. All right, so you know how to define, therefore, the energy of the system, QW. All right, rearranging the heat in. Ay, ito pala. Sorry. So this is Q in. This is the work. Okay. And this is the energy added to the system by mass flow in and mass flow out. Okay. So this is our energy. So later you will see this enthalpy reaction as we define the flow of mass in and out, because what is going out, of course, energy that's coming out will be a fraction of that is part of the energy of the end of the reaction, heat of the reaction. So let's take the individual component of this energy. And since you know already enthalpy as a state function, okay, we will be working on and you know internal energy to define the energy of the system. What is that energy of the system? Internal energy plus the flow energy, the flow work. Okay, the this energy here represents an internal energy, the microscopic energy of the system. If you consider yourself as the system, your body has what we call internal energy due to your what cells, body cells. So these are the microscopic form of energy due to the molecules that comprises the system, that's always in transient motion, vibrational motion, and then there's rotation, friction, and so on. So whatever is happening in your system is a measure of your internal energy, whether it's kinetic energy of the molecules or potential energy as they move from higher or lower energy level. And also part of that will be, of course, the kinetic. Okay, so that's the totality of your microscopic form of energy, the kinetic and potential of the body. So that's the internal energy. So you know how to define internal energy, class? The macroscopic and the microscopic form of energy. All right, and then this energy as well, aside from the totality of your microscopic form of energy within your system, within your body, okay, it is also due to an energy that is caused by flow of fluid in and out of the system, because you're trying to push your system that's coming in the reactor at a given pressure 1 with a given volume 1, and then you try to push the system out of the reactor. So that push in and out, pull out, gives you some sort of energy change, which is the pressure volume change. Because when you push, you add energy to the system to push it inside. So that is the flow of fluids, right? The flow of fluids, for the fluid to flow, you have to cause delta P, a certain delta P. There will be driving force for fluid to flow. And that push requires some sort of an energy. And that pull also requires some form of energy. Of course, delta P is what? For pumping. It's always P1 is always greater than P2 for a fluid to flow from point 1 to point 2. So this requires some form of energy that has been added to the system as it goes in and out of the reactor through the piping system. Okay, so this is what we call the flow energy. And so much for that, class. Since you have done, I think you have done this already before, the flow energy and that of the microscopic energy. Follow, class? All right,
Yes.
so we need to dissect all of that, definition of flow work and other work. All right, this work here as well. So the flow work includes that. Okay, so the work that is needed by the system includes the pressure volume work and that of the mechanical work added to the system. So that consists of that. So in that case, we have the work term into and out. So other works include the shop work, which is this, if it requires mixing. But most of the time, it's going to be negligible in most of our calculation here. So the work requires pressure volume work. So internal energy represents the energy of the system represent mostly internal energy, and the work represents the shaft work and that of the flow work, which is the pressure volume. So you will see from here that this energy here of the system that is incoming and outgoing consists of that uh, pressure volume work. That's additional energy, and that of the shop work. Okay, so sorry, not that energy yet. Okay, we will dissect that. So that work represents a measure of the flow rate, okay, of SPCI and okay, and in, okay. So flow rate out is, why is it positive? Flow rate in is negative. Push. Work is done by the system to the surrounding. Okay, let me deal with the sign convention because this is negative work. And so when you say negative work, so when we say work, that is um, in is always greater. PV in is always greater minus PV out. Okay, PV out is always lower. And so that is work. And so multiply by negative. So that gives us the negative P in, positive P out. So negative times negative becomes positive for this one, plus the shop work. So this is the work component. And so let us work faster so we can finish this slide. So this is the work component, and the sign convention has been changed because in this energy balance, work is going out, our sign convention. So you have that. So of course, work and volume. So you have then the component of energy of the system. Okay, energy of the system, accumulated energy in the system. So heat minus other work plus energy and work added by flow in, energy and work removed by flow out. So we can combine, okay, this energy here, flow work in the energy in and flow out in the energy out. So combining that, since we're talking of the same species coming in and out, wherein we push those coming in and push out the coming out, okay, with the pressure P out, okay. So combining that in this energy term, so analyzing the energy term again, we're talking of the system internal energy, the kinetic energy of the system that I am discussing. And if the system velocity is considered and the displacement as it flows from the horizontal, say, plug flow reactor, there is usually, for a steady state process, velocity 1, velocity 2 at point 1 and 2, inlet and outlet is considered negligible. And so the displacement is also negligible since delta C is 0 for a horizontal flow. So that will be the totality of the energy of your system coming in and out. So, and other energy, the magnetic, electric, and usually that's negligible as well. So that internal energy, the energy of the incoming and outgoing species will just have to be simplified as internal energy. And then Therefore, the internal energy plus that of the pressure volume work, we know how to define that, right? So we define that as your enthalpy. Okay, so that's how we do your energy balance, a detailed energy balance, so you can understand better how you do your energy balance for your non-isothermal reactor design. So again, simplifying further, we can proceed much faster, class, right? Any questions so far? So instead, we are now defining enthalpy instead of U plus PV, combining those two. So enthalpy now. So later, we will define now enthalpy of the reaction. All right? Now it's leading to defining enthalpy. Now enthalpy of the incoming species at temperature T sub O. Remember class that your reactant will be coming in the reactor initially at a temperature Ti sub O. Now Ti refers to the individual species entering the reactor. So maybe species 1 will be entering separately with the species 2, okay, B. All right, so that's why maybe the temperature of reactant A will be different from the temperature of the reactant B. So that's why it's Ti sub O. All right, so that will be Tb sub O, and this is Ta sub O. Maybe they will be having different incoming temperature, but then most of the, say, if the reaction will involve solution of A and B, all right, therefore they will have an initial temperature of the mixture or solution. So it will just be T sub O. So you don't really have to specify individual species temperature coming into the reactor. Is this clear, class? All right, so you will see that later. So it could be part of your simulation reactor wherein you have varying input temperature of the reactants or solution. So T sub O, all right, is the incoming temperature of a feed solution, or T sub O is the incoming temperature of the individual species of the reaction. So incoming reactant species, okay, and outgoing reactant species. So that will be at a temperature Ti sub O. And this is the final temperature of the reaction as the reaction is taking place from, say, V sub O to a final volume, if you're talking of a PFR. Anyway, so this will now be the overall energy balance. For a steady state process, again, this accumulation inside will be 0. Okay? Meaning to say, whatever is the incoming minus outgoing heat in the reactor is the same as the heat is equivalent to the heat that is flowing in and out due to the outgoing species, all right, and incoming species. So there's no accumulation of the heat inside the reactor. So at steady state, all right, so that will be the case. So whatever is the difference between in and out here would be the same energy. That should be, if this is input heat, all right, of the surrounding. So you're talking of energy balance, right, of the universe, small universe, the system, and the big surrounding. So your system is your reaction taking place in the reactor. And then you have the incoming feed and outgoing product. Okay, and this is isolated from the surrounding. So adiabatic. All right. So it only means that whatever heat is coming in and work that is done out, so that difference will be the heat absorbed by the, for example, heat is added. So that is heat absorbed by the reaction. Okay, and that must be equal to the flow of heat in and out of the reactor. Okay, so that's the difference. So the surrounding Q plus that of the reaction Q, all right, must be, the sum must be equal to 0. All right? Or we can say that whatever is the heat needed by the reaction will be used up by the reaction. Okay. Para yung ano naman, no, calorimeter, whatever is heat added to the water must be the same as the amount of heat that is given off by the reaction. So that is the same idea. Did you get it, class? This is the first law of thermodynamics. Did you see the first law here in this energy balance? The surrounding heat coming from the surrounding, the total energy of the universe must be 0. The surrounding energy plus that of the system energy must be 0. The heat given off by the system is the amount of heat that must be absorbed by the surrounding, or the amount of heat supplied by the surrounding must be the same amount that must be absorbed by the system. So that sum of plus or plus 1 or minus 1 Q, that represents that the total energy of the universe is constant. All right? Follow, class? So you see now the first law application in this reactor, an open system reactor, okay? So this is the statement of the first law of thermodynamics in an open system, okay? Follow, everybody? So this is how you see your energy balance or application of the first law of thermo in your reactor design. Now, let's proceed further. Now, this is just an indication that, okay, so what is this flow of species leaving the reactor? This represents the product, right? So this represents the species leaving the reactor, and the molar flow rate of the species I leaving the reactor represents your product and the unreacted reactant. So that represents the how much is therefore its say for a reactant, for example, a reactant species. It is usually say FAO, initial flow rate of A. Since there is flow rate, so we're talking of the flow of say moles of A per unit time, say per unit second, and how much will be reacting. So minus the coefficient of A, which is say stoichiometric coefficient of A represented by A, and then multiply that by how much is used, how much is converted. So so that will be this amount based on the initial amount, and this is the conversion A, and based on the balance equation, this is the amount of A needed for the balance reaction, for the reaction itself. So amount that reacted. So initial times the conversion. But of course, you need to specify also that there's a limiting reactant. So based on the exact amount of A that will be reacting, so you have to multiply by A. Usually A is 1. In this case, A is 1. Because we want to normalize our reaction, for example, in such a way that our A is always treated as the limiting reactant. So this is B over A times B. So that is always V sub I. Okay. Ay, hindi pala. It's not, sorry. So sometimes you can treat A, you can normalize, and so you get V over A. So A will have a, what you call that, the coefficient 1. But in this case, VI is based on the balance elementary reaction. Okay, based on that reaction stoichiometry, so V represents the coefficient based on the balanced reaction. So it's positive for product, negative for reactant. So that means to say this is initial minus the amount that reacted. So this is the flow rate of the species that will be leaving the reactor. Okay? And so F sub I, factoring out your Fi, and so Fin is Pc divided by FAO. So everything divided by FAO. So you get the term pi, alright? FAO. So divide everything by FAO, this equation. So F sub I now is defined in terms of FAO multiplied by 1 kasi ito no? Multiply by 1. So you leave out in the factor out the FAO. So bali, that is multiplying the equation by 1 is still the number. You won't change it if you multiply by FAO over FAO. But then again, you distribute the FAO in the denominator here. Okay? So you don't have it here. So given that, so you have FAO therefore remains outside. That's the factor. And this is your second factor, which is FIO is the ratio of the flow rate of any species aside from FAO over the FAO. So again, FAO is assumed to be our limiting reactant, and so plus V sub I, of course, multiplied by XA. So this is now the simplified representation of flow rate of any species coming in with respect to the flow rate of the limiting reactant, which is FAO. Is this clear, class? So in Fogler, we have make use of the term pi, okay, to represent the flow rate, initial flow rate of any species with respect to the limiting reactant A, initial. Okay, so that is our convention. That's the definition of pi. Pi sub I. All right. So what time na? Ako, puro pa to derivation. Okay, and all right, class. Can you still follow our derivation, class? This is very important, class, because understanding the parts of your differential equation later, whether you see a plug flow, CSTR, batch, you can derive any energy equation with this. All right, then let me proceed faster na, since this is a review of thermodynamics supposed to be. All right, therefore, we have to represent again the overall energy balance, replacing our F sub I in terms of FAO definition, in terms of the, because we want to express the concentration in terms of the conversion XA, all right, in the energy balance. So FAO times pi times quantity pi plus that. So remember, this is also a pi. All right, something common. So multiply. All right, distribute. Sorry. So we can move faster in a class. Are you following this, class? So we are going to define our enthalpy reaction later. So when we are defining our, when we distribute the FAO to the two terms and then obtain the common factor here, there's a common factor. You can see FAO na green, factor out, and then we have the summation of the enthalpy now. Okay, so this is where you see the enthalpy. Okay, let's picture out this group of terms of enthalpy. How do you picture this? Picture this one, class. Imagine, how do you see this in the reactor, class? I have here the reactor. All right, this is how I represent the temperature of the incoming species, all right, as it enters the reactor. Okay, so this is the enthalpy of the species entering the reactor. And then later you will correlate that to the temperature of the species entering the reactor, right? And so once the species enters the reactor, it will have an enthalpy H sub I. And as soon as the species enters the reactor, it will have a temperature T. And this is the variable T as the reaction proceeds, okay? That's the variable T. All right. So there will be changes in temperature of the reactant. Okay, so as soon as the reactant enters the reactor, this is now the temperature of the reactant at the start inside the reactor. All right, so there's what we call delta T, some sort of delta T here. Okay, so that's delta T. All right. So delta T means this is the change in temperature as the reactant enters the reactor from T sub I O to T inside the reactor. Follow, class? So that represents the heat needed for the reactant temperature to change from T sub I O to the reactor temperature T sub R at the start. Okay, and therefore, as the reaction proceeds, the reactant temperature inside the reactor that is unreacted will have a temperature, whatever is the temperature inside the reactor, T of the reactor, that is variable. Okay? So that is the T changing within the reactor as the reaction proceeds. Follow, class? And
Yes, po.
okay, very good. So that's how we see this, how we picture this group. Okay, this is how we picture this group. And then the next group. Now this is V sub I. So remember when we say V sub I, it's positive V sub I for product and negative V sub I for the reactant. Follow? Negative V sub I for the reactant. So the summation of V sub I product minus reactant will be the enthalpy of your reaction multiplied by the conversion. Whatever is the conversion will be the amount of the heat of the reaction that is produced per mole of the reaction. So that represents the heat of the reaction. Okay, let's proceed now to our final equation then. So we have defined already the last two terms. One is related to the enthalpy of the reaction calculation, and then the other one is the heat required for the reactant temperature to change from TiO to T sub I. T sub I inside T inside the reactor, temperature inside the reactor. So let's see. Again, we already know how to define enthalpy of the reaction from your FICChem. Enthalpy of the reaction, since this is a state function, so you can easily define this in terms of enthalpy standard plus the delta Cp of the reaction changing from T to T reference, okay, plus enthalpy standard. Okay, so I will not discuss that in details anymore. So this enthalpy of the reaction is defined already. We know how to define that from as a state function, because there's no way we can directly measure enthalpy of the reaction, so we have to change the path of your reaction, bring down the temperature of the reactants from T of the reaction to T reference, where you can measure the standard enthalpy reaction at the reference temperature, which is 25 degrees Celsius or 298 Kelvin. So you can have the reaction at that temperature, 298. And then once you produce the product, you have to bring it back up to the temperature of your final product. Okay, now that is how we define enthalpy of the reaction. This one, the standard enthalpy, of course, is always a function of the standard reference temperature plus that of the enthalpy of the Q reaction for formation of the individual species. So this one is a more detailed discussion of enthalpy of the individual species, but then based on some reference temperature. Okay, but then I will not cover that anymore. So enthalpy at the reference temperature. Okay, so this is just a simple definition of so in short, I will just give you the final enthalpy of the reaction, which you already know how to get. If the individual species is defined in terms of the enthalpy, and enthalpy is defined in terms of heat capacity, wherein the heat capacity is a function again of temperature. So given that, so enthalpy of the reaction will be based on the standard enthalpy of reaction based on the standard enthalpy formation of product minus reactant plus the enthalpy of the uh, heat capacity at constant temperature of the reactants and products from T to T sub R. Okay, so you know how to define this already. Question here, class. So you know na this one, di ba? Because our reaction at T, all right? So this is enthalpy of the reaction that you want. But we cannot get that directly, so we have to bring down the temperature back to that. And so this is the enthalpy reaction standard at this point, and this is the CP reactant, and this is your CP product. So this is how you obtain. So this is your reference temperature, and this is your temperature, the delta T. So this is that delta CP. Okay, so this defines the enthalpy of your reaction. Follow, class? Wag na natin anuhin yung napaka-detail na discussion ng delta H. Okay? But you can read that na lang. So, everything is based on a reference temperature. And then magka-cancel out naman lahat. Alright, so we already know how to estimate enthalpy of the reaction given this one. You need to know the CP of products minus CP reactant. So this is one example. Alright, so let's proceed. Parang slide 1 pa lang tayo. 4:30 to 6. I only have 30 minutes. Okay, let me proceed now with this. This is just estimating enthalpy reaction. So we already know how to do this in Thermo 1 and in kinetics, ba? Okay, so enthalpy reaction is calculated given the heat capacity of the products and reactants. So this is one example. Of course, everything is based per mole of the reaction. So in this case, per 1 mole of nitrogen, this enthalpy of the reaction at any given T is calculated based per 1 mole of nitrogen that reacted based on the balance equation here. Or you can define this per 3 moles of hydrogen or per 2 moles of ammonia. That is per mole reaction. But of course, you want to know how much is the exact amount of nitrogen that reacted. It's not 1 mole, right? But if it's maybe if it's only 3 moles, if it's 3 moles that reacted, so you have to multiply to get the total heat of the reaction, you have to multiply by 3. Or if it's only 0.5 moles that reacted nitrogen, so you just have to multiply this by 0.5 moles. Okay, the exact amount of nitrogen that reacted. Okay, so in this case, this is per mole of hydrogen. There's 1 mole of nitrogen that is available, and there's 3 moles of hydrogen. So in terms of hydrogen, so you get only 32.5 per mole hydrogen. So anyway, enthalpy again is what we call ano yun? In this case, this is per mole. So ano yun, class? Intensive property. If it's extensive, you have to multiply by the quantity, how much reacted. Now, in this case, phase change at Tm, solid to liquid. So enthalpy of the reaction, if there is enthalpy change or phase change, so the enthalpy has to be, if it involves phase change, so the enthalpy of the reaction has to be recalculated based by adding a certain heat of phase transformation. So that will be this reaction. So if the reactant is solid, and once, for example, a reactant that is solid and it enters the reactor that is very hot, so that's solid now. Okay, so this is what is happening when we have the enthalpy calculation. If the reaction has phase change, so this enthalpy formation, of course, the reaction. What is taking place is that the enthalpy of the reactant that is solid, okay, And then once you enter the reactor, that reactant becomes, say, liquid or maybe gas, or in this case, liquid. There are reactants naman like used oil for biodiesel. It enters the reactor as liquid. As soon as it enters, it becomes vapor. So there's heat involved in the transition from solid to liquid. So heat must be added. Heat must be absorbed by the reactant. Q absorbed by the reactant as it transforms its phase from solid to liquid, or maybe from liquid to gas. So this is that energy, delta HM. All right, so that's the heat capacity of the solid is known if you want to see that, and then delta T. So heat capacity of the liquid is known as well. So you have enthalpy of melting, in short, enthalpy of melting from at a constant temperature. Okay, so that will be at a constant temperature at the temperature of the reactor. So there are a lot of energy involved. So energy, that heat that is involved from so Q1, sorry, in changing the temperature of the reactant from TiO to T. And so once the temperature of the reactant is already at T, and then that is still liquid at an instant, or maybe solid at that instant, then eventually it becomes this solid becomes liquid, or this liquid becomes vapor. So transition is happening at constant temperature T of the reactor. So this requires additional Q, or maybe heat given off during that process, or in this case, solid, liquid, liquid, vapor. Heat must be added. So that will be the additional, the heat that must be absorbed by the reactant. So usually that absorbed heat is usually taken from the heat of the reaction. All right, so when you take energy balance in a reactor, part of the heat of the reaction is actually used to convert the phase from solid to liquid, or maybe it's part of the heat that is added to the system, so that the temperature of the reactant will be heat may be absorbed by the reactant as it changes its temperature from TiO to T, as the heat is coming as supplied to the reactor, and therefore that also causes the phase of the reactant to change. So that's the heat that is involved. Or maybe the heat of the reaction is causing the phase of the reactant to change, or temperature of the reactant to change as well. So that could be happening inside your reactor. So you have to take into consideration all the energy involved in the reactor. Okay? So this will be the phase change. If there is phase change, this will be the individual heat at the reference temperature, and then from the reference to the melting. And then this is actually important if you are going to do simulation, and if your problem requires heat transition from the reference temperature to the melting temperature. So you bring it up to the melting temperature, and then nagmelt at the delta T, and then there's melting at constant temperature at Tm. Okay, that's the transition now. If it involves the enthalpy of melting, and then there will be now the transition from the melting to the temperature of the reaction. So that will be that. So Cp, from melting to the temperature of the reaction. And this is the reference temperature. Okay, could be that way na lang, para straight line. So reference temperature. So this will be all the heat involved for the enthalpy of the individual species, if it's going to be a reactant or a product. Usually, of course, reactant, this one. Or the product could also have changes in phase. So But most of the time, it's the reactant that has to change the phase. And some of the product may also vaporize. From the liquid product, it becomes gaseous product. So all components that will be changing phase should involve this summation. So that way, our phase change now. So instead of having the, in short class, and I'll not make a detailed discussion of that. So if it involves phase change, okay, we have to refer to enthalpy, okay, enthalpy definition. All right. So in our energy balance, okay, so we have to define again your Q minus WS. And so for the third term again, this is most of the time the incoming species, there's no reactant, there's no product. Therefore, the summation of pi Cp refers only to the product. So there's no reactant. There's no product involved. So P sub I is this. Okay, so simplifying now our, so if there is a phase change, of course, the enthalpy is expressed as enthalpy initial and final, and enthalpy of the reaction. Of course, this is your enthalpy is defined also in terms of heat capacity. Okay. So overall, this is our energy balance. So this is now our enthalpy for the reaction. Okay, multiply by the amount of the species that reacted based on the initial amount of the limiting reactant, because this is always per mole of reaction. So say per mole of A. So how many moles of A is produced? So this is equivalent to the amount of heat that is produced by the reaction. Okay. So eventually, you can have two forms of this, with phase change and without phase change. So how do we consider energy balance with phase change and without phase change? Okay, so this will be our condition later. Again, that enthalpy, that pi, usually if there's no product, it has to involve only. Okay, all right. So again, this is our final equation, right? If the product, or if the reactant will not undergo any phase change, so this is good for your energy balance. If there is phase change for the reactant, so you have to express everything in terms of enthalpy. All right, so that's the difference between the two types of reaction, with phase change and without phase change. Usually for most reactants coming in, entering the reactor. Okay. All right. So any questions of our class? So you see now, the energy accumulation again, if it's 0, if it's steady state, this one is 0. Q, WS, most of the time this is 0, so later you will see this will just cancel out later. But this is our general equation when there's no enthalpy, when there's no phase change for the reactant. So if the reactor is at steady state, which term in this equation would be 0? Again, nasabi ko na pala, class. Okay. Ang dali naman ang clicker question natin. Okay. Okay, ang tanong ay madali. Okay, nasagot na natin. Okay, that is the question, the answer. Anyway, at steady state, therefore, here. Now, if there is no phase change, again, the form of this equation, the third term, is this. Okay. Of course, the enthalpy of the reaction, you know how to get the enthalpy of the reaction already. So this is our energy equation. Dito hindi masyadong define. So in Fagler class, you will see a table. All right, you will see a table for the summary of the heat equation of the energy equation for CST RPFR for adiabatic, and you will see that for adiabatic process, CST RPFR will or any reactor will have the same TX formula. Okay, so this is where you get your TX formula. This is the temperature. Though if we will not eliminate this delta Cp, our temperature formula will be more difficult. But if we can eliminate this, our T expression versus X will be less complicated. All right. So this is actually our energy balance that represents our T and X relationship. Though this is here, usually this is negligible in most of the time. So you can easily express T as a function of X easily, okay, on that. If not, you have to derive. Although it's derived na naman, class. I just have to show you how we derive this working equation so that you can have an expression of T and X, so that you can understand better this definition, this term, okay, this term, you can understand this better, you can picture this better, and then you can understand this better. And then you can see again the definition of the first law of thermo, that the energy of the universe is zero, is constant, because this is the energy of the surrounding plus energy of the system. Diba? Kung energy of the surrounding is plus 10, energy of the system is negative 10. Plus 10, negative 10 equals to 0. Alright? So you can see minus, minus, so plus, so minus energy of the system. They are equal. Energy of the system and the surrounding are equal for steady state operation. Follow, class? So that's the big picture of the first law of thermodynamics in the flow process, flow reactors. Alright then. Medyo di ako aabot doon sa... Okay, how do we handle Q in a CSTR? Bakit nag-adiabatic na ito? Non-adiabatic. Okay. Later na yung class na energy equation. Later na lang yan. Adiabatic muna tayo. Hold on, class. It's already 17:51 and I only have 9 minutes for this. So, alright. So I'll just have to show you again the final equation for a CSTR adiabatic process. Oh, okay. From the energy equation, this is that energy equation. But then again, before that, I guess, hindi pinakita dito yung energy balance. You can actually read this lecture, the second lecture, and then you can also read the lecture from our book on the summary of TX relationship. Ito pala yan. TX relationship for non-isothermal reactor design. So from here, class, you can have a review of our enthalpy. Okay. Okay, definition, enthalpy of the reaction, initial temperature of the feed. Okay, and so solving TEB for conversion. So this is actually the definition of XA as a function of T. Alright, so for an adiabatic process, therefore this is Q. This Q is 0. And most of the time, WS is 0. So that's why see the derivation of the TX relationship in Fugler, okay, for adiabatic. So this is actually that relationship. Okay, from the overall energy balance that we defined earlier, which is this. So this is 0. So we just have to obtain this t as a function of x. So this is how we get that. So I will not discuss in more details that process. So we have here your so when q is 0, okay, so this is where we assume adiabatic operation. Okay, and so read this lecture, class, and so next meeting will continue na lang. And hopefully I could finish the second problem that we have for the non-adiabatic. Alright, so simplifying, this will be the temperature energy balance, temperature energy balance for XA for an adiabatic reaction. Okay, so let's work on this next meeting. Alright, so non-isothermal CSTR and application, given this equation for case 1, application to steady-state PFER, adiabatic as well. So we will cover this next meeting for non-adiabatic CSTR and PFR. So for today, you have learned already how we derive all this equation, and then we will apply again your integration techniques. In this case, this is just a simple 2-point rule. You already have 4-point rule. What is 4-point rule, class? How do you derive that 4-point rule? Class? In your integration, 4-point rule, 5-point rule pala. Meron tayong 2-point rule, 5-point rule. 5-point rule is derived from Simpson's 1/3 rule, which has n, wherein n is 2, wherein each segment is divided into multiple segment, 2 multiple segment into 4 segment. All right, the area of a Simpson's 1/3 rule, each segment is divided into 2. So overall, you have 5-point rule in that segment. So you can do that. That's how you define 5-point rule. So your integration by Simpson's 1/3 will be more accurate. So that is the Simpson's 5-point rule. Follow, class? Because you have here 2-point rule, we have 5-point rule. Okay. So study this example and the other example, which is found in our lecture. I uploaded already one problem exercise and posted already one problem set. So we will finish this discussion next meeting then. All right, any questions so far, class?
Ma'am?
Yes.
Ma'am, would the assigned assignment for this lesson be moved to next week po?
Yes, it will be moved next week kasi medyo mahaba yung discussion natin ng energy balance. Anyway, with this discussion, class, you are now confident that you can do energy balance for a CSTR, PFR, and any type of reactor. Are you confident now, class? Yes?
A bit.
Marvin, no? Sino ba itong kausap natin? I think you're now confident to do energy balance and material, though it's more on energy balance and material balance for any reactor. Right, Ron?
Yes, ma'am.
Very good. So just don't forget how we do that. This is simply first law of thermodynamics. That's how you apply first law of thermodynamics. But of course, this is a flow reactor design. So flow reactor design. So it's very important if you're going to work particularly